Ever wonder how AI got so good at understanding images? Like really, really good.
It's mind-blowing.
Totally. So today we're diving into the research paper that kind of like cracked the code.
You mean the ImageNet Classification with Deep Convolutional Neural Networks paper?
That's the one. It's like the Sherlock Holmes of computer vision, you
Ah.
know? And trust me, this case is a wild ride.
This 2012 paper, it didn't just win awards, it completely changed the game.
Okay, so set the scene for us. What was the big mystery they were trying to solve? What's the case all about?
Imagine this. You want to build a program, a computer program, that can identify 1,000 different objects.
1,000.
1,000. Everything from, like cats to castles.
Okay, 1,000 different things.
The problem is, well, how do you even begin to teach a machine to make sense of that much visual information?
Right, because it's not like you can just show a computer a flashcard and be like, this is a cat, right?
Exactly.
So how did they crack it?
They cracked it with scale. Massive, massive scale.
Okay, I'm intrigued. Tell me more.
So they used a data set called ImageNet,
ImageNet, right.
which had over 1 million labeled images.
1 million images?
Over 1 million, yeah, spanning 1,000 different categories.
Wow, 1 million images. That's like, I don't know, showing the computer the entire photo album of the internet back when that was still, impressive.
Exactly. And that scale, it was unheard of at the time. It was the key ingredient that allowed them to train a model that was complex enough to handle this challenge.
Okay, so they had a mountain of data, but then how did they actually turn that data into intelligence? That's where these convolutional neural networks, or CNNs, come in, right?
Precisely. Think of a CNN like like a digital assembly line, but for processing images.
Okay, a digital assembly line. I like that.
Yeah, so each layer of the network, it looks for specific features.
Specific features like what? Give me an example.
Like edges, textures, shapes.
Okay, so like the basic building blocks of an image.
Exactly. And then it builds upon the previous layer's findings. So it goes layer by layer.
So it's like those early layers are picking out the rough outlines, and then it gets more and more detailed as you go deeper into the network.
You got it. You're getting it. And the beauty of CNNs is that they learn these features themselves directly from the data.
Oh, wow.
The researchers didn't have to program in rules like look for whiskers to identify a cat.
That's amazing.
The CNN figured that out on its own just by analyzing millions and millions of examples.
That's incredible. So it's not just mimicking how we see. It's learning its own way of understanding images.
Exactly.
But it wasn't just the CNN architecture that made this paper a game changer, right? I mean, they had a few more tricks up their sleeves, didn't they?
Absolutely. They introduced some, well, I'd call them ingenious training techniques that are honestly still fundamental in deep learning today.
Okay, I am ready for the secrets of their success.
Right.
What were these groundbreaking techniques?
One of the key breakthroughs was using something called ReLU.
ReLU?
It's a simple mathematical function, believe it or not, that dramatically sped up the training process.
ReLU, faster training, got it.
Yeah.
But how does a simple math function make such a big difference?
It all comes down to efficiency. Without, getting too deep into the weeds, ReLU simplifies the calculations the network has to make.
Okay, so it's doing less work, essentially.
In a way, yes. Which means it can learn much faster from the data.
Got it.
It's like taking the scenic route versus finding a shortcut. You get to the same destination, but one way is much, much quicker.
So ReLU, like a shortcut, sped things up. What other tricks did they use?
They tackled overfitting.
Overfitting. Okay, now there's a term I haven't heard in a while.
Right. So imagine a student who memorizes the answers for a test
Okay, I can imagine that.
instead of actually, understanding the material.
Yeah, been there, done that. Not the best strategy.
Exactly. They might ace that specific test, but they won't be able to, generalize that knowledge.
Right.
And it's the same with AI.
Oh, so how do you stop an AI from basically becoming a test-taking cheat?
You introduce a little bit of chaos.
Chaos.
Chaos, but in a good way.
Okay, I'm listening.
They use a technique called dropout,
Dropout.
which randomly turns off some neurons during training.
Turns them off. Like, it literally just shuts them down for a bit.
Exactly.
Wow.
It's like forcing the network to rely on different parts of its brain.
Okay, so it can't just use the same pathways every time.
Right, and not get too comfortable with any single pathway.
Got it.
So this makes the model more adaptable and less likely to overfit.
So it's learning to think on its feet, like finding new connections. It's like
Yeah.
the difference between, I don't know, one-trick pony and like a seasoned performer. You know what I mean?
That's a great way to put it.
Right.
They didn't start there, though.
Oh, there's more.
Oh, yeah. They also used a technique called data augmentation.
Data augmentation. Okay, break that down for me. What is that all about?
Okay, so imagine you're, trying to teach someone to recognize a chair.
Mhm.
You wouldn't just show them a picture of a chair from one angle,
And
right?
of course not. You'd show them like different kinds of chairs from different sides, maybe even some upside down, just to mess with them.
Exactly.
Ah,
With data augmentation, they did something similar with the images. They flip them, rotate them slightly. They even, tweak the colors a bit.
so they're showing the model all the different ways an object can look in the real world. Like, a chair is still a chair, even if it's upside down.
Precisely.
Clever.
This made the model much more robust and um, much better at recognizing objects in, all sorts of diverse situations, just like you were saying with the chair example.
Okay, so they had this massive data set, this like revolutionary network architecture, and then these really clever training techniques. It's like they were stacking the deck in their favor.
Yeah.
But did it pay off? I mean, what happened when they unleashed this model on the ImageNet Challenge?
It blew the competition out of the water.
No way.
The error rates they achieved were they were unprecedented at the time. For most images, the model correctly identified the object in its top 5 guesses.
So not just a win, like a landslide victory.
Yeah, pretty much.
Okay, but I'm guessing this paper wasn't just about bragging rights. Like, what was its lasting impact?
Honestly, it's hard to overstate the significance of this research. It wasn't just about recognizing images. It was about proving that deep learning could achieve human-level performance on a complex visual task.
So it opened the floodgates for all sorts of AI breakthroughs, like
Yeah.
all the stuff we're seeing today.
Exactly. This paper, it really laid the foundation for the incredible advancements we're seeing today. Like, self-driving cars,
Right.
medical image analysis, even, facial recognition software. All of that has roots in this research.
It's like they didn't just climb Mount Everest, they built a staircase for the rest of us to follow.
I like that analogy.
Ah, cool.
And here's where it gets even more interesting.
Oh, there's more.
The researchers, they didn't just want to know that their model worked. They wanted to understand how it worked. They wanted to, peek inside its artificial brain.
Okay, now we're getting to the good stuff. How do you even begin to, dissect the mind of a machine?
Well, they found a way to visualize the features that the network was learning.
Visualize. Okay.
Yeah, so remember those layers we talked about? Each one picking up different patterns?
Uh-huh.
They found a way to actually see what those patterns look like.
Wait, so they could actually see what the AI was seeing in a way?
In a sense, yes. And what they found, it was fascinating. They could see that the early layers were indeed, picking up on those edges, those basic shapes, just like we talked about. But the later layers, they were learning to recognize much more complex features like textures, patterns, even specific parts of objects.
It's like they were able to map out the AI's thought process, like layer by layer.
Precisely. And this ability to visualize those features, it wasn't just a cool party trick. It gave researchers a powerful new tool to understand how these models actually work to, diagnose problems and to even improve their designs.
This paper is like a masterclass in deep learning. We've got a groundbreaking architecture, clever training methods, these impressive results, and then this whole other level of insight into how the model actually thinks. I'm exhausted just talking about it.
It's truly remarkable work. And it's a testament to the researchers' vision that so many of these ideas are still relevant and, widely used in the field today.
It really makes you appreciate how far we've come in such a short time. This paper was like a launch pad for the AI revolution.
Mm.
But then it also kind of makes you wonder, where do we even go from here?
Right.
What happens when we start digging even deeper into these mysteries of artificial intelligence? We've gone from decoding hieroglyphics to translating fluent alien languages in a decade.
It's an exciting time to be working AI, that's for sure. This paper really opened up a whole new world of possibilities.
And with new possibilities always come,
Yeah.
new questions.
Always, yeah.
What do we make of the fact that we can now, I don't know, it's like we can peer into the mind of a machine, at least to some extent.
It's a profound thought, isn't it?
It really is.
We've gone from wondering if machines could ever think to actually analyzing the way they learn, the way they process information.
It's almost like we've created this new form of life almost.
Yeah.
One that learns and evolves in ways we're just beginning to understand.